Welcome, everyone. Let's get started. Course announcements. Problem set 6, the final problem set, is out on Slack, and I'll be putting it in my courses. It is due December 4th. I reposted it today because I realized, thank you, Ivan, that there was a typo and the algorithm in problem 5 needed to be, you should be finding a polynomial time algorithm. That is the only change, just saying that problem 5, you should be finding a polynomial time algorithm. And then a clarification about the schedule, the way that the class schedule works at McGill. There will be 4 more classes after today. They will be this Friday, next week on Monday, Wednesday, and Thursday. Thursday is on a Monday schedule. Are there questions about that or anything else in the course? So again, the problem set will be due on the Friday after the last class. I will still have office hours on that Friday as normal. I don't know whether Vincent will have office hours next Thursday. That's a really good question. Post about that in the Slack or email him. I think posting in the Slack would be great because then everybody will be able to hear the answer. I'm not sure whether Vincent is on a Monday schedule or on a Thursday schedule. Okay, let's get started. So today we're going to be looking at approximation algorithms. So we've been considering decision problems, which are, again, yes or no valued problems. They're either a yes or they're a no. And often a decision problem will come with a similar optimization problem. For example, we were looking at whether there is a clique of a certain size, but you could also imagine trying to find the largest clique, or the smallest vertex cover, or the smallest cost for a Hamiltonian cycle. And in general, there are a lot of optimization problems that also don't come with decision problems, where you are trying, or where the optimization problem is typically what you're trying to solve. When a decision problem is NP-complete, there is often an associated optimization problem that's similarly hard or even harder. So for example, we were previously looking at whether there is a vertex cover of a certain size. If we could find the smallest vertex cover, then we could solve the NP-complete problem of determining whether there is a vertex cover of size k. Why could we do that? Well, if we could find the smallest vertex cover in a graph, then there are 2 possibilities. Either the smallest vertex cover has more vertices than k. In that case, there definitely isn't a vertex cover of size k because the smallest is bigger than k. If the smallest vertex cover is smaller than or equal to size k, then definitely there's a vertex cover of size k because you can just add more vertices to get a vertex cover of size exactly k. So I guess the point I'm trying to make here is that if you have a decision problem and an associated optimization problem, a maximization or a minimization problem, then typically that other problem, the optimization problem, will also be really hard because it might be able to solve the decision problem for you. So it's like at least as hard as the decision problem. However, sometimes we can find an approximate answer to an optimization problem much faster, even if the problem the corresponding decision problem is NP complete, for example. So if we're allowed to sort of relax the problem a bit. Now, the reason why I'm talking about optimization problems here, not decision problems, is there isn't really a relaxation to a yes-no problem, to a decision problem. You can't say, there isn't a way to soften that, but there is a way to soften an optimization problem. And this is why one can talk about approximation algorithms. For some row bigger than 1, we can say that an algorithm is a row approximation algorithm if it gets within a factor of rho of the optimum. So you can say, well, maybe I didn't get exactly to the optimum, but I got most of the way there. I got within a factor of rho. So for a max problem, that means that you need to get at least the optimum divided by rho. So for example, if rho were 10, then if you had a 10 approximation algorithm, you would be like, okay, well, I have to get at least optimum divided by 10. And for a min problem, I would need to get at least, sorry, I would need to get at most the optimum times rho. So if it were a 10 approximation algorithm for a minimization problem, then I would have to get within a factor of 10. And getting within a factor of 10 means, in that case, that I'm not going to, that I'm at most 10 times the optimum, that I'm within a factor of 10 of the optimum. So this is just sort of intuition. There's a question. This is not on average right. Exactly correct. This is not, it's not an average. This is like you have an approximation algorithm if you just always get within that amount of the optimum. Now, we will look at randomized approximation algorithms in a few slides where it is on average. But for the moment, we're just looking at normal approximation algorithms, which are deterministic. And your goal is to get within a certain factor of the optimum. More questions? Are the optimization problems related at all to things like convex optimization? They absolutely could be. An optimization problem is just maximizing or minimizing something. So there certainly could be situations where what you're trying to maximize or minimize is a convex function, or they're with all the constraints being convex. You could absolutely have that situation. So there are different ways of looking at optimization problems, and we're going to be actually looking in a slightly different perspective in a couple of classes. But for now, we're looking at approximation problems for sort of things that to solve exactly would be like NP hard. Okay, let's dive in. So here's a reminder of one of our NP-complete problems, vertex cover. Given an undirected, unweighted graph, G, a vertex cover of G is a set S of vertices such that every edge of G has at least one of its endpoints in S, possibly both endpoints. So a vertex cover is just making sure that every edge in the graph includes at least one of the vertices in your vertex cover. You're covering, in some sense, all the edges of the graph. And then again, here are some examples of vertex covers, which are the vertices shown in red. So here, every edge in the graph touches at least one of the red vertices. So this one touches 2 red vertices, this one touches just 1. But you never have an edge with 2 black vertices. Another way of thinking about it is that the set of vertices outside the vertex cover must be an independent set. There are no edges between 2 black vertices here. And again, last time we actually used the fact that the things outside of a vertex cover are an independent set in order to prove a reduction from click to show that vertex cover is NP complete. So we defined the problem last time, vertex cover of GK, as the problem of determining whether G has a vertex cover with K vertices. And we saw that vertex cover is NP complete. Now let's look at an approximation algorithm for this, but we need to define the corresponding optimization problem, and it sort of makes sense. Vertex cover is a decision problem. Let's look at the corresponding optimization problem, min vertex cover, problem of finding the minimum size vertex cover, or a minimum size, because there might be several ones with the same size. Let's come up with a two approximation algorithm for min vertex cover. And again, what does that mean? Well, sorry, this should be at most. I really messed this up. Since this is a minimization problem, we need to come up with a vertex cover where the number of vertices is at most, again, I'm sorry, this should read at most, optimum times 2. We need to be off by at most a factor of 2. Are there any questions about this? We'd like to come up with the smallest possible vertex cover, but that's going to be hard. So let's come up with an approximation. So we're off by at most a factor of 2. So it's possible the algorithm yields an answer bigger than n. So if the vertex cover is more than half the size of the overall graph, then it's really easy. We just take all the vertices. But the vertex cover might be smaller than half the vertices of the graph. For example, it's possible that one vertex will cover all of the edges. Okay, so let's find a two approximation algorithm. So given a graph G, let's construct a vertex cover S, one vertex at a time. Let's take an edge of G. And let's add both endpoints to the set S. And then let's take out, so we've added those two vertices to the set S. So we now know that any edge that has either V or W in it is now covered. So let's just take out all of those edges from the graph. Those are now no longer in consideration. So here we have our original graph. Here we've picked an edge. We say, OK, we take both of these vertices and we throw them into our set S. And we delete all of the edges that touch either of those vertices because we know they're covered. Now we find another edge in the graph, not one of the ones we took out. Let's pick this one. So this one we now add. And we add both of these vertices to our set S. We take out all the edges connected to either one of those new vertices, E or F. And we repeat. And here we find another, there's only one more edge left in the graph now, so we take that one. So again, we pick an edge in the remaining graph, add both endpoints to S, remove all the edges including either endpoint, and iterate. After a while, we get nothing but isolated vertices. Like the end condition is there are no more edges to add. So in this case, we've added 3 edges, 6 vertices to S, and we have 1 vertex that we didn't add. Because it's isolated. It was never part of an edge that we added. So in this example, we've taken every vertex in the graph and we put it into our set S, except for the isolated vertex A. But in general, we might have a lot more isolated vertices. Like, it's possible that every one of the vertices in the graph was connected to either B or C, in which case we would have taken out one edge, put two vertices into S, and we would have been done. We would have only ever put two vertices into S, and there could have been a lot more vertices in the graph. Are there questions about the algorithm? How to determine the order? So we could make it just be random, but there's no need for it to be random. We could just suppose that the edges of the graph are given to us in some order. We just pick the next edge. Like whenever we've got, it doesn't matter what the order is. It doesn't have to be random. Like just literally any order will work. Good question. Okay. So this is, again, our algorithm. Take an edge, throw both of its endpoints into S, remove all the edges, including either of the endpoints, repeat that. And after a while, we end up with nothing but isolated vertices. No more edges to add. Why is this a 2 approximation to the smallest vertex cover? Yeah, so suppose that we have a minimal vertex cover. And let's call this S star. So for example, a minimal vertex cover here could be B, E, and D. Every one of the edges in this whole graph is covered by one of B, E, and D. Now, if we have this minimal vertex cover, it must contain at least one of the endpoints of each of the edges we added. So we added 3 edges, BC, EF, and DG. Now, those are edges in the original graph, which means that any vertex cover has to have at least one endpoint from each of those. And since the edges are completely non-overlapping, we know that those endpoints are different, right? So like, there is at least one of these endpoints, and at least one of these endpoints, and at least one of these endpoints. And they're all different. And since we added 3 edges, there have to be at least 3 vertices. And in this case, B, E, and D, that works because B covers this edge, E covers this edge, D covers this edge. And they also happen to cover all the other edges. But at least we know that they cover the edges that we ourselves found in our algorithm. So we took 2 vertices from each of the edges. But we know that the minimal vertex cover has to contain at least 1 vertex from each of the edges. That means that S, our cover, contains at most twice as many vertices as the optimum. Because each time we added 2, the optimum had to have had 1 of them. Questions? Is this a valid vertex cover if it still has isolated vertices? Great question. So the reason why it's a vertex cover is because the isolated vertices happen because we took out edges. We take out an edge when it's covered. So like there was an edge here. We took it out because it was covered by B, once we added B to S. If there were literally a vertex that never had any edges, so it was never connected to anything, then you could still have, you wouldn't need it in your vertex cover because the point of a vertex cover is to cover all the edges. You don't need to worry about isolated vertices. Does that answer your question? Again, I guess I skipped a thing, which is important. There are two things you need to show when you're showing an approximation algorithm. Thank you for keeping me honest here. The first thing you need to do is show that you actually found sort of a legal solution. So here we need to show that it is a vertex cover. It's sort of clear that it's a vertex cover because we're only taking out edges from the graph when they are covered by the vertices we've put into S. So when we've taken out all the edges, we're like, okay, all the edges were covered. But yeah, so there are two components. First, showing that it actually is a legal solution, and then showing that it's close enough to the optimum. So it's a legal solution in this case because it's a vertex cover. And it's close enough to the optimum because whenever we added two vertices, we add pairs of vertices to S, the optimum has to have had at least one of them. So we must be fine. Now, this also should tell you that it's pretty easy to get an approximate vertex cover, at least within a factor of 2. And in many cases, the vertex cover will be large enough that a factor of 2 is like the size of the graph itself. So, but in some cases, in some cases, this will actually be very few vertices if you have some very central vertices that are connected to a lot of the rest of the graph. More questions? In this particular, wouldn't you be able to just pick the entire graph with the same upper bound? No, actually, in this case, we had 3 was the optimum, and 6 is within a factor of 2, and 7 is the size of the entire graph. So if we picked the entire graph, we wouldn't have been a 2 approximation algorithm. We would have been we would have been a 7/3 approximation algorithm. To find the exact cover, can we try all the exponential choices? So, I mean, yes, in this particular case, it is possible to find the exact solution by just trying exponentially many things. This particular solution, though, is pretty fast. So let's look at that now. This is the algorithm. How long does it take? It depends on how exactly you're encoding the graph, but it's definitely polynomial time, which should make us happy. Like in these last few lectures, we're just caring about polynomial time versus not polynomial time, except in this case, kind of it's nicer because it's linear time. I've written down big O of V plus E, the reason being that sometimes V will actually be bigger than E. For example, if there were very few edges in the graph. But in general, E will be bigger. In general, E will be bigger than V, so it's O of E, as people were suggesting in the chat. And that's just because we are basically going through the edges. I mean, we find a new edge that we didn't take before. We delete all the edges that are connected to one of its endpoints, which is very fast to do if we have, depending on how we've stored our edges. If we've stored our edges as like for every vertex, we already have a list of what it's connected to, then it's very easy to delete all of those edges, and then we can just proceed in linear time. I'm not going to go into the details of that, though. More questions? Can we make any graph format assumptions? So the reason why it's like, sometimes you will want to store a graph in different ways, depending upon what you are trying to do. For example, I will never ask you to do a problem that requires you to assume that the graph is stored in a particular way. Like on the problem set, I was just saying things polynomial time, and that doesn't matter how the graph is stored. But yeah, sometimes you'll want a graph in like as an adjacency matrix. Sometimes you'll want a graph so that like you have just a list of what every vertex is connected to. The reason why there isn't a single best way to do it is it depends on things like aspects of the graph. It's a really good question. So if you have a dense graph, so a dense graph means that the number of edges is close-ish to the number of edges that you could have. So it's basically like number of vertices squared. If you have a dense graph, it makes sense to store it as an adjacency matrix. But if you have a sparse graph where, say, the number of edges is like linear in the number of vertices, you would never want to do that because the adjacency matrix itself takes up space, which is quadratic in the number of vertices because it's an n by n matrix. So if you only have n non-zeros in an n by n matrix, it makes sense just to list them all out, basically. So it really depends on whether you have a sparse graph or a dense graph in particular. And then particular graphs, you might have more compressed ways of storing them too. Or more useful ways for a particular context. I hope that answers the question. OK, let's move along. Can we always find all the edges connecting to a vertex in constant time? You can if the graph is stored that way. If the graph were stored in an adjacency matrix, you might have to do a search along the row of the adjacency matrix, and it might take you number of vertices time. So if you were working with a sparse graph in an adjacency matrix format, this algorithm would take quadratic time, I guess. But you probably shouldn't work with a sparse graph in adjacency matrix format. If you're not getting all of these details, don't worry about it. It doesn't matter for the context of what of what we're covering today. OK, let's move on. So we've talked about deterministic approximation algorithms. We can also think about randomized approximation algorithms. So we've already seen one randomized algorithm, quicksort, or at least there are different ways of doing quicksort, but we saw a version of quicksort where we were picking a random pivot and recursively sorting lists. And the randomness sort of helped us do it well. So let's take a look at other random algorithms for this. Random algorithms, sorry, I should say, that help us solve problems fast. Sometimes we will want to have a randomized approximation algorithm. But we need a different notion of approximation algorithm if we're going to have our algorithms be potentially randomized. So what is that? What is the new notion of approximation algorithm that we need here? Well, previously we said that we had to get within a factor of rho. Now we can say that we have to have the expected value of the output within a factor of rho. So each particular time we run it, it might or might not be within a factor of rho, but the expected value is going to be within a factor of rho. So again, for a max problem, you would need to have the expected value of the output be at least the optimum divided by rho. For a min problem, you would need to have the expected value of the output be at most the optimum times rho. And again, that's just sort of intuitive. If you're within a factor of 10, that means if you're trying to have a max problem, then you need to be at least a factor of 10 below the optimum. And if you have a min problem, then you're always going to be above the min. So you have to be at most a factor of 10 above the optimum. And I guess something that I didn't note before, for randomized and non-randomized algorithms, rho is always something that's greater than or something equal to 1. You wouldn't have like a 1/2 approximation algorithm. You would write it as a 2 approximation algorithm, if that makes sense. So You're always, whenever you say an approximation algorithm, the factor that you give is the thing that's greater than 1. So if you had something that's less than 1, then you take 1 over it, I guess, if that makes sense. It wouldn't make sense to have something be less than 1 here, because that would mean you were doing better than the optimum. OK. I guess, are there any questions about this? Just the framing of a randomized approximation algorithm. It's just the same as an approximation algorithm that isn't randomized, except with expected values. OK. So as a review of 3SAT, so we previously looked at Boolean formulas, and we looked at Boolean formulas in 3 conjunctive normal forms, so 3C and F. And there are a series of clauses separated by this wedge thing, which means and, where each clause has 3 variables or their negation separated by the V, which means or. And or. So here's an example, which happens to have 3 clauses. Because it's in 3 conjunctive normal form, each of the clauses has 3 variables. They're separated by ors. Each clause is separated by, the individual clauses are separated by ands. So this clause has to be true, and this clause has to evaluate as true, and this other clause has to evaluate as true in order for the whole formula to be true. In the formula, again, and an or I talked about, each of the variables is Boolean. It's either true or false, and negative just means the negation of the variable that you flip true and false. OK. Now, 3SAT was the problem of determining whether a formula, which is in 3 conjunctive normal form, has any solutions, i.e. something that satisfies all of the clauses. And this is an NP-complete problem. So let's look at a related optimization problem. In some sense, relaxing. Well, no, this is not. We're not relaxing it yet, but we're giving ourselves an optimization problem that enables us to relax the problem. So define max 3SAT as the problem of determining the maximum number of clauses that can simultaneously be satisfied in a 3 conjunctive normal form formula. So for example, if we looked at that formula we saw before, we can actually satisfy all of the clauses. The entire formula is satisfiable. But if we had n different clauses, then it's possible that we couldn't satisfy all of them, but we could satisfy almost all of them simultaneously. So if something's not satisfiable, then it's in some sense like, how close can we get to satisfying the whole thing? We get to pick which clauses. We just like, how many clauses can be satisfied? What's the max number? Now, if all of the clauses can be satisfied simultaneously, then the problem is satisfiable. And that means basically that what we're doing here, max 3SAT, is at least as hard as 3SAT. Because 3SAT is basically a special case of max 3SAT, where we say we can just like run max 3SAT with all and see if we can satisfy all of the clauses. If we can't satisfy all of the clauses, then we know that the answer to 3SAT is no. So again, we have an optimization problem, which is actually, like, on the face of things, harder, at least it is at least as hard as 3SAT. Questions about this? Let's also assume, just for the sake of simplicity, that we aren't ever in the situation where each clause, where one of the clauses has some of the same variables. If it does, then we just can throw that out, because sorry, not throw it out, but it is no longer necessary to consider it. So like, if you have x1 or not x1, well, that is always true. Sorry, I guess I shouldn't have said, I didn't mean to say impossible clauses here. I meant to say always true clauses. So the opposite of impossible. This clause is always true because x1 or negative x1 is always true. If x1 is true, then this thing evaluates to true. If x1 is false, then this thing evaluates to true. Yeah. So yes, trivial clauses, I should have said. I will correct that in the notes. No trivial clauses like this. Questions? Again, we're trying to find the maximum number of clauses that we can satisfy. So let's find a polynomial time randomized approximation algorithm for max 3 set. And we're going to get pretty close. Remember, the best we could do for an approximation algorithm is factor of 1, which means we exactly got the optimum. Let's find an 8/7 approximation algorithm. Feels like a bit of a random constant, but we'll see why in a moment. So this is a max problem. So we need to have the expected value of the output be at least the optimum divided by our constant here, which is 8/7. So yeah, again, another way to think about it is we just need to get at least 7/8 of the optimum. If we got 8/8, we would have reached the optimum. If we got more than 8/8, we would have been exceeding the optimum, which is impossible. But we're trying to get almost to the optimum, so 7/8 of the value of the optimum. So we have some formula, which we're trying to satisfy. It's a formula with a number of clauses in the variables x1 through xm, which are, again, true or false. Each of the variables is true or false. And in order for the formula to be satisfied, we have to have all of the clauses evaluated as true, but we're trying to just maximize the number of clauses that are true. How could we try assigning the variables? Bearing in mind that this is a randomized approximation algorithm, what is the, in some sense, stupidest thing that we could possibly do? Dynamic programming is far too complicated. So there's a suggestion to set all of them to true. I think that is actually the stupidest thing that we could do. Unfortunately, like I want one step above that. But yeah, setting them all equal to true would be the absolute stupidest, simplest thing. So you are correct. What if we just assign them randomly, like completely random, true versus true or false? Yeah, and there are smarter ways where you could imagine like you set some, and then based upon what the clauses are that aren't satisfied yet, you assign some others, and that could certainly help. But let's just think about what happens if we assign all of them completely randomly. So we want the expected number of clauses that are satisfied, and we want this to be at least 7/8 of the optimum. That would be our goal here for our approximation algorithm. So remember, we're trying to we look at have an expected value here, right? Whenever you see an expected value, think about linearity of expectation. Think about how you can break the thing that you're trying to calculate the expected value of into things that you know how to calculate. So how could we break up x, which is the number of clauses which are being satisfied? Oops. There's a question from in the chat. If we have less than 8 clauses, will this always be the optimal max? Then, so the expected value doesn't have to be an integer. So the expected value could be between 7 and 8. Or it could be, yeah, it could be like, it doesn't have to be an integer. The expectation that one clause is satisfied. So this is a really good way to do things in general with expected values. Imagine that you have an indicator function where a value, your variable xj is just 1 if clause j is satisfied, and 0 otherwise. This is what we've done in a lot of situations with linearity of expectation. We take a thing which is the number of things which happen, and we break it up into, did this one happen? Did this one happen? Did this one happen? And even if the things depend on each other, then linearity of expectation, the magic of linearity of expectation, I can't say this enough, means that we can calculate the expected value of the sum as the sum of the expectations. So in this particular case, we have the expected value of x being the expected value of the sum of all of these indicator functions. Did clause 1 get satisfied? Did clause 2 get satisfied? All the way down to clause n. And that can just be the sum of the expected values. Now, what is the expected value of xj? More generally, what's the expected value of an indicator function? So the expected value is just the probability that the clause is satisfied. That's just what an expected value is if something is 1 or 0. It's just the probability that it is 1. So let's work out what that is. So remember that a clause is the OR of 3 different variables or their negations. So it's true if this thing is true, or if this particular one is true if x1 is true, or if x2 is false, or if x4 is false. Sorry, if x4 is true. Any of those can be true. We don't have to have all of them. We just have to have one of those things be true. So the probability that this is satisfied is the probability that at least one of the 3 variables or their negations is true. At least one of these 3 things has to be true. That just corresponds to, we're flipping 3 coins, the probability that at least one of them turns up heads. And what's the probability that at least one of 3 coin flips is heads? Yeah, so I like the way to think about this as, I mean, you could calculate it as the probability that one of the 3 coin flips is heads, plus the probability that 2 are heads, plus the probability that 3 are heads. But you could also just write this as 1 minus the probability that you have no heads. Probability that you have at least 1 head is 1 minus the probability that you have no heads, because either you have no heads or you have at least 1. So what's the probability of no heads? Well, the probability of no heads is the probability of getting 3 tails. All of them are tails. So you have 1 minus 1/8. So in 7 out of 8 cases, you will have at least one head because only one of the 8 possibilities you have no heads. So let's go back and plug this in here. We're looking at the probability that clause Cj is satisfied. And that's just the expected value of the expected value of xj. So the total expected value is the sum of the expected values of the xj. So it's the sum of 7/8. And there are n clauses, so we have 7/8 of n. That is the expected value of x. Questions? This is just a completely random assignment. So what we're trying to do was we're trying to have an expected value of 7/8 times the optimum. We actually did even better than that. We have an expected value of 7/8 times the total number of clauses. We need to, it's possible that not all the clauses can be satisfied. It's possible the optimum is not all the clauses, but we could satisfy 7/8 of the clauses just by a completely random assignment. An expectation of 7/8 of the clauses, I should say. So therefore, we have a random 8/7 approximation algorithm. And in fact, it might be, it might be better than that because the number of clauses, the optimum, might be less than all of the clauses. Questions? Now, that doesn't mean that any particular random assignment is going to work. It just means that the expected number of clauses that we satisfy with a random assignment will work. And now here's a nuance. There's an interesting corollary of this approach, which is that there has to be a setting of the variables with at least 7/8 of the clauses satisfied. So what we showed was that the expected number of clauses that we satisfy with a random algorithm was 7/8 of the clauses. Now, that doesn't. We can show from this algorithm is that for every formula, there is a way to satisfy at least 7/8 of the clauses. There's no randomness here. It's not that we are expected to have a setting of the variables where 7/8 of the clauses are satisfied. It's because there must be a setting of the variables where at least 7/8 of the clauses are satisfied. Even if we can't find it, there has to be one. Assuming that there aren't trivial formulas, yes. There are no trivial clauses where you repeat the same variable. Though honestly, that could just make it better. But if you had x1 or x1, that would make it potentially worse. Why is this true? Why is this statement true? Why does there have to be a setting of the variables where at least 7/8 of the clauses are satisfied? No randomness in this statement again. This statement is just there is a way to satisfy at least 7/8 of the clauses. Don't know how to get there, but there is one. Why is it true? So we know that if we randomly assign values, true or false, to the variables, then we end up with an expected number of 7/8 of the clauses satisfied. Right? That was what our previous algorithm showed. Now we're trying to show that there has to be a particular setting where 7/8 of the clauses are satisfied. But our random assignment, what is an expected value? An expected value is just averaging over all the possible ways to assign true and false to the variables. So if you average over all of those, the 2 to the m possibilities, you have to get 7/8 of the clauses being satisfied. But what this statement is saying is that the max is at least 7/8. But the max is always at least the average. So if we're averaging over all of the possible settings and we get at least 7/8, then the max has to also be at least 7/8. And in particular, there has to be some setting of the variables where at least 7/8 of the clauses are true. We never actually found that, but we know it exists. This is a super powerful way of proving things, showing that the expected value of something is a certain amount, and then showing that there has to be something which is at least that expected value. Even if you can't get there, you know it exists. I will stick around for any questions. And in the meantime, here is a poll about the speed of class today. Good luck with the problem set, and I will see everybody on Friday. Again, if you didn't hear at the start of class, there are 4 more classes in the term. They are this Friday, next Monday, Wednesday, and Thursday. Office hours for me are as normal. I don't know about Vincent's office hours next week. Thanks, everyone. See you in a couple of days.